Kia ora, it's Mrs. Goodson here. I hope your day's going well. This video is about periodic trends. So it's this second video about the content for Chemistry 3.4. The learning intentions of this video is to learn how to state the trends in the periodic table. So the periodic trends, there's three parts to this: atomic and ionic radii, ionization energy, and electronegativity, and how to compare the atomic and ionic radii. And radii is just the plural of radius. So radius is singular, one radius, many radii. So I'm actually going to do three different videos. The first one is on, this one is about atomic and ionic radii. And then I'm going to make two different videos, one about ionization energy and one about electronegativity. So this is the periodic table, and it was developed 150 years ago by the Russian chemist Dmitry Mendeleev. And so he is the inventor of the periodic table. And as over the last 150 years, our understanding of how important this is and how it relates to everything in the universe, all materials, all matter in the universe, has become even more important. So the periodicity refers to the similarities and characteristics and properties of elements based on their position in the periodic table. So we look at the trends across and down and what the periodic table can tell us about the properties of these elements. The first thing we're going to look at is atomic radius. This is the size of the atoms calculated from the average distances between neighboring atoms. So it is, if we've got two atoms and they've got the nucleus, is the distance between these nuclei. Remember, the radius is half of the diameter. Okay. So we're just basically talking about the size of atoms and ions. Okay. So here is a periodic table. As we go across a group, so we've got a row or a period. So a period is a row here and a group is a column. Okay. So the size of the atoms is affected by the atomic number. So the obviously the more protons and electrons, the bigger the atom's going to be. And the nucleus will have more protons, so it will have a higher positive charge. As you add electrons, as we go down the periodic table, we're adding electron shells. It also means more valence electrons. And what we want to think about is the electrostatic attraction between the nucleus of an atom. So if we draw an atom down here, we've got the nucleus, which is positive, and the electrons on the outside are negative, and then there is an attraction between these, between the positive and the negative. So this is the nucleus. The stronger the attraction, the closer the valence electrons are the ones on the outside, the closer the electron's going to be. Okay, so as we go along the periodic table, the charge on the nucleus is going to increase because there's more protons. Shielding is the effect. So this is the nucleus here. And then we've got the electron of interest, which is our valence electrons. The electrons outside the valence electrons, if there's any electrons out here, they have no effect. We're not interested in those at all. The nucleus has a positive charge. The electrons between the outside ones and the nucleus, they are negative, remember? Just like these electrons are negative. So what happens is they actually repel each other. So there's some repulsion going on, electron repulsion here. So electron repulsion. And they actually shield. So we remember there was a attraction between the positive and the negative. But if there's lots and lots of inner electrons, what happens is they shield the nucleus from the outside ones, and they also provide repulsion. We can think of it as repulsion between the electrons in the inner shells and the valence electrons. So this affects the size, because if the attraction between the positive and the negative is reduced by the shielding or the electron-electron repulsion, then the outside electron is going to be further away and the atomic radius is going to be bigger. Okay, so across a period or a row, for example, from sodium to argon, the trend is it decreases. Okay, so that sodium is a bigger atom than argon. So across a period, the atomic radius decreases. The atomic number increases because there's more protons. The electrons are being added to the same energy level. And so the electrostatic attraction between the nucleus and the valence electrons increases because there's more protons, more plus, but they're at the same energy level. So the valence electrons are pulled closer to the nucleus and the atomic radius decreases, so the atoms get smaller. So across a period, the atomic radius decreases, and then you need, and this is the reasons. So you need to be able to state the trend and then give the reasons. Moving down a group, so a group is a column. Where's my thing going? So we've got down a column. So as you go down a column, the atomic radius increases, so that you need to know the trend. The positive charge of the nucleus increases. Again, bigger atomic number as you go down, the more protons in the nucleus. The valence electrons are further away because as we go down a group, we're adding electron shells. And so therefore, there's more shielding by the inner shell electrons. And that means that the electrostatic attraction between the nucleus and the valence electrons is going to decrease, and therefore the radius increases. Okay, so again, you need to know the trend. Moving down a group, the atomic radius increases, and then you need to be able to give the reasons. For example, I want to give you an example. So lithium is here, lithium and sodium. So we're moving down the group from lithium to sodium. The electron configuration for lithium is 1s2, 2s1. And for sodium, it's 1s2, 2s2, 2p6, 3. So we've got 2, in lithium, we've got 2 electron shells. And in sodium, we've got 3. We're starting to fill the third electron shell. So the atomic radius increases due to an extra electron shell. So that would be going down a group, for example. So for ions, so ions are atoms that have lost or gained electrons. So metal atoms like aluminium, they lose electrons to form positive ions. Do you think the radius is going to get bigger or smaller? Remember, it's lost electrons. It's lost electrons. However, when it comes to making a negative ion, that's, for example, this nitrogen is going to gain electrons. Is the radius, so we're gaining electrons. We're going to put them in the same electron shell. Then is it going to get bigger or smaller? So what happens is the positive, so going from an atom to an ion, aluminium loses electron, actually loses an electron shell. So it's going to end up smaller. Whereas the negative ion, going from an atom to an ion, it gains electrons, and so it actually ends up being bigger. So here's some examples. So have a look at, this is group 17. So we've got fluorine going to fluoride, gaining electrons going into the same shell. So monatomic ions, ions made up of only one ion, are calculated from the measurements of ionic crystals. Okay, that's how they're written out. So metal atoms, groups 1 to 3, lose all their valence electrons or outer shell electrons as they form positive ions. This results in one fewer level of electrons. So these positive ions always are much smaller. Now here's an example to explain what I mean. So we've got sodium atom, and it's going to sodium ion. So we might compare, why does sodium ion have a smaller radius? We need to be able to explain that we have actually lost this, we've lost this electron, and so there's fewer levels of electrons, so we end up with smaller radius. Compared with negative ions, like chlorine going to chloride, they gain valence electrons as they form negative ions, and so they're always larger because of the increased repulsion between the increased number of electrons in the valence shell. So for example, the chlorine atom has 3p6, the chloride ion has 3p8. So there's more electrons, but they're in the same shell. So the radius is not getting bigger, but no extra shells. And so there's increased repulsion, electron-electron repulsion between the increased number of electrons in the valence shell. Okay, so there's the positive monatomic ions always will be smaller than their atomic counterpart. So the positive ones are always going to be smaller, the negative ones are always going to be bigger. There are more protons, and so there's a stronger pull from the nucleus. And the negative ions, negative atomic ions, always be larger than their atomic counterpart. There are more electrons, a weaker pull. So the shielding or the electron-electron repulsion has decreased the electrostatic attraction between the nucleus and the outside electrons. So there is a weaker pull, a weaker force from the nucleus. Okay, here's an example exam question. Why the radii of so the question asked, explain why the radii of the sulfur atom and the sulfide ion are different. Okay, so they gave you this information. They said the atom was 104 picometers. That's really, really small. Compared with the sulfide ion, which went to 184. So the ion was bigger. Okay, so it's going from the atom to ion. It's a negative ion. So in the mole answer, it says that sulfur and the sulfur ion have the same number of protons, but when the sulfur atom gains 2 electrons to form the sulfur ion, there is increased electron-electron repulsion in their valence energy shell. As a result, the electrons move further apart, and therefore the sulfide ion has a larger radius than the sulfur atom. So in this answer, you needed to describe the difference between the sulfur atom and the sulfide ion, which the differences and similarities. So they have the same number of protons. You would include how the ion is formed. In this case, it gained 2 electrons. You need to give the reason that the radii are different, which was increased electron-electron repulsion, and then link it together and say, and so therefore, that's why the ion had a larger radius than the atom. So that is an example of an exam question on this topic. And we're going to look at further questions and further videos. And so this video was about the atomic radii and ionic radii. And the next videos will be about ionization energy and also electronegativity. Thanks.